are my fault campaigns providing accurate result for ISO 26262 certification. Abstract. Running an efficient fault campaign with accurate result can be difficult task, especially in large complex designs, but optimizations and techniques exist to make it less so. The satisfactory result may have been attainable in the past, but in the increased size and complexity of the automotive design and its difficulty in providing good quality stimulus and a large number of faults and need to be analyzed, make it practical to perform exhaustive safety verification using a single technology. Unfortunately, there are many methodologies that provide efficiencies for running for the campaigns, starting with the early and accurate safety analysis. Using a safety analysis tool, the structural analysis RTLN provide accurate safety metric such as FIT and DC, allows engineers to understand the safety level of their design and reach the optimal safety architecture prior to costly fault injection. This paper will discuss these techniques using the Samsung safety flow methodology as a real-world example. It will outline real use cases and discuss the importance of the accurate metric during the analysis phase of the flow, outline the 48 optimized techniques, and propose recommended to set up the condition for optimal stimuli, and discuss when a good machine simulation is needed based on Samsung certification activity. Section 1, Introduction. In the paper, the complexity safety mechanism requires interpolatables automation for validation and metric closure. Presented at the DVCON US 2023, we covered the fundamental methodology to overcome the typical fault campaign challenges for SOCs with the complex safety mechanisms, whereas the paper describes the general methodology and flow for fault campaigns. I did not go into the details of how to plan and verify the fault campaign activity. The questions not addressed in that paper include: how do we know the fault campaigns we are doing are providing accurate result? Are we running fault campaigns that represent real use cases? That the stimulus behavior at the RTL providing the result at match the final gate level analysis result. What are the different techniques available to accelerate fault campaigns? Do we need a good machine simulation for all the stimulus at all levels of SOC development? In this paper, we attempt to answer these questions and identify what is the required in fault campaign methodologies to achieve the accurate result for ISO 26262 certification. We further explained what we should be considered to make sure the good quality stimulus is generated for fault campaigns, how to grade and stimulus quality checks prior to running fault campaigns, and how to implement a methodology for a good machine simulation. The fault simulation is resource intensive. At a minimum, you need to simulate a good machine and the faulty machine, and the good machine is used as the difference to determine if any faults are detected. Good machine simulation is where all state elements and observation points are compared to all times in the original stimulus to catch a dominant deviation. The good machine simulation is a systematic way to ensure the stimulus is to good quality and provides accurate result, and good machine simulation can solve the missing simulation data problems and reduce the load on the functional verification team. To create a stimulus that provide accurate result at both RTL and gear level, engineers need to make sure that the stimulus has minimal to race conditions and no behavior mismatches between the simulation and synthesis. Making sure the good stimulus is used for fault campaigns and having the right type of the set of conditions to generate the stimulus to test the real use cases is critical. An integrated set of tools such as simulation and emulation fault injections also accelerate fault campaigns runs, as we will illustrate with the Samsung design. Additionally, the older the gear level simulation is more accurate and more closely represent the silicon behavior using RTL models is an acceptable approach, providing the RTL code used is shown to be well correlated with the gate level netlist, and the kaleidoscope and Siemens EDA concurrent fault simulator utilize a pseudo synthesis method for RTL simulation. This means that in this essence, we are running the level fault campaign. Another important aspect of efficient fault campaign is making sure that the fault lists are optimized. We automatically create optimized and customized fault list for appropriate engine and a long concurrent and parallel fault injection runs on use all available compute power to reduce the cost of fault injection. The fault optimization techniques used for a Samsung design include safety mechanisms aware, fault collapsing, and statistically random sample. The safety mechanism aware optimization eliminates the fault that are not part of the safety mechanism cone of the influence (COI). So the fault collection will eliminate logically equivalent fault, and the statistical random sampling allows you to reduce the fault list of size of the random sampling of fault estimated given a confidence level. All these methodology for optimization fault list were considered. The section 2, good quality stimulus. There are several steps to making sure the good quality stimulus is used to get an optimal result from a fault campaign. To generate the proper stimulus, several conditions must be considered. Correct design setup, forces in the test bench, RTL simulation, versus the thesis mismatches, XPROP, reserve, and racing handling. The correct design setup. When using the stimulus generated for a good machine checks for fault campaigns, we need to make sure that we have a correct setup. The design should be the same between the functional stimulus generation and good machine fault campaign simulation. The fault quality stimulus, we need to make sure to use the same input configuration, including file list, defines parameters, and preloads into memory. Forces in the test bench. A complete list of the forces that were in the functional simulation needs to pass to the fault campaign engine. A force on a signal engine net to propagate to whether the net goes across the all hierarchies as shown in the below example. Figure 1 is valid force value propagation through design for a fault campaign. And the figure 1, the force in the net is shown in the red circles. The effect of this force should be propagated to the out of the gate 1, which will affect gate 2 and flip-flop 3. The force value propagated cannot stop at top dot inst underscore 1 or top dot inst underscore 1 and inst underscore 2. The forcing behavior can be different between the RTK11 netlist. Synthesized netlist behavior is closer to silicon, and because synthesized design has a flattened net similar with the silicon. RTL and the pound, the sharp delays. When a sharp delays, doing a functional simulation is always a good practice to avoid putting sharp delays in RTL as shown in the figure 2, because adding delays will result in a simulation versus synthesis mismatches in the functionality of the design. The figure 2 sharp delay is in RTL. To make sure to avoid any inadvertent sharp delay, stimulus generation should always use a non-sharp delayed modeling. All the industry standard simulators have configuration for this. In this case, the original code already has lots of sharp delays. Additional handling is required to guarantee valid fault campaign result. The simulation behavior versus mismatches. Simulation models mismatches occur due to the discrepancies between the simulation model and the hardware behavior. These discrepancies can cause an unexpected result, which can occur due to the incorrect logic or improper design implementation and the RTL. Some examples of the effect of this behavior are missing synchronizer between the clock domains, improper simulation models that do not match the final hardware implementation, out of indexing of the data arrays, mismatching between the address pointers and data location size. To avoid this situation, we recommend using the lint clean RTL for stimulus generation. Any industry standard linter can be used to achieve the good result. XPROP reserve in RTL stimulus generation. RTL simulation uses the value of X to temporarily represent a state cannot be predicted or determined at a given time because X values do not appear in the design once it has implemented in the silicon. A mismatch can occur between the simulation and the silicon. Typically, RTL simulation is done based on X optimization, but it reflects the silicon behavior more closely. X pessimism is preferred when debugging X behavior in a simulation. This also be one of the best practice can show the use to RTL code related with the gate level analysis. When using RTL for fault injection testing, consider the following code in Figure 3. X optimism and X pessimism code example. The table 1 shows the simulation result for both X optimism and X pessimism. Result for X is the behavior of the X pessimism. Test table 1. Simulation result of the node of the X propagation, known X propagation versus X reserve mode. Use X the reserve in RT simulation to attempt to reserve X values via forcing them to deterministic state based on a certain algorithms or resolution rules. This helps in modeling how the hardware might behave when encountering unknown state. It also provides a better insight into how the synthesizers would behave when encountering the unknown state and aids in the caching the issues that might arise due to the gate level optimization or mismatches between the RTL and gate level, represented as shown in Figure 4. Figure 4. X propagation and simulation result on box design. Race conditional stimulus. As races can cause deviations in a simulation behavior, the most common races are reset to clock race. This race condition happens when a test bench changes resetting the clock at the same time. This can be avoided by changing the slab when the clock is active. When we have observed this is fairly hard things to do in complex test benches, we added a feature to Siemens kaleidoscope tools to delay the reset until the reactive clock edge is observed. Data to clock race. This happens when a test bench drives data on an active edge of the clock. To avoid this, data should always be driven in an inactive edge of the clock. If the user does have a clear way of handling this, to take advantage of the feature of the used simulator can be used when generating stimulus. So for example, Siemens digital simulator provider data D race clock data switch for simulation. It can mitigate the race between the clock and the data and provide a way to read all the stable data values. Section 3. Good machine simulation. A port campaign tools in a good machine simulation must check to see all the state elements of the design are matching with that of the input stimulus. This includes the checking of observed point or state element for deviations. Checking observed point. Limiting the check to only observed point will compromise the correctness of fault campaign result because the dormant deviation of the state element can result in incorrect behavior. Critically checking all state elements. The kaleidoscope fault simulator checked not only observed point but also state element for deviations. The benefit of this methodology is that avoids the dormant deviations since kaleidoscope is checking all statement element and observed point of deviations for resulting the campaigns are always accurate. Kaleidoscope approach to machine simulation consists of the following. Check deviation at the observed point. Check deviations of all statement element, flip-flops and latches. Check deviations of memory content. Check all dormant deviation and fault campaign based on correct goal simulation. Chapter 4, Fault Campaigns. We propose the fault campaigns methodology that addresses the correctness of the rightness of the campaign. Following this methodology shown in Figure 5 guarantees that a fault campaign is right the first time. Figure 5 is for campaign methodology. This corrected stimulus generation for Ford campaigns as described in section 2 of this paper. Also look at the description for active safety mechanism below. Do good machine simulation GMS to check all internal statement elements and observe the point to avoid the inconsistencies as described in section 2 of this paper. Pick the best stimulus to shorten the Ford campaign time by using stimulus rating as described below. Run Ford campaigns with correct design and stimulus setup as described in section 2. The active safety mechanism. Doing Ford campaign on a stimulus where the safety mechanism of active is detrimental as it will result in a marking or the fault as undetected. It is very important to activate all safety mechanisms in the design to Ford campaigns. A good approach is to put a self-checking in place in the when implementing the safety mechanism, which will copy the behavior of the fault and will trigger the alarm on the safety mechanism. Use these steps. Add an injection capability in the safety mechanism. Use this capability to see the proper alarm trigger. Clear the error injection and clear the alarm. A safety mechanism is now ready to use. Checking the safety mechanism activation with the classified detected fault result. The simulation grading. The simulation grading is a technique where all input stimuli are analyzed to pick up the one that allows performing the most fault injections. This can be as simple as looking at the toggle coverage, or it may involve the propagating fault to the next statement element to see if the deviation propagated, which is more complex than looking at the toggle coverage. The race condition is a stimulus. We talked about how important it is to make sure the hand race conditions and generating stimulus for fault campaigns. In the same way, it is very critical to also make sure to handle race conditions in the fault injection flow so the results from the fault campaigns will be consistent. The XPROP equal reserved. As discussed, we strongly recommend generating stimulus using the reserved as propagation method. Section 5 is test data analysis. Good machine simulation deviations. In the Samsung design, the initial good machine initial simulation analysis showed quite a good deviations. After taking care of stimulus generation issues, these deviations went away. The initial stimulus was generated with the XPROP equal no XPROP, which resulted in 15% of the total state elements deviated. We generate the stimulus with the XPROP equal reserve and used the good machine simulation. The deviation percentage went down to 4.63%. We did not stop here, and we wanted to understand all the deviations to see if we could fix or understand them. In the next section, we will discuss our approach to this. Table 2 is XPROP body experimental result in good machine simulation. Resolving remaining deviations, the remaining 4.6% deviations were analyzed in several categories. The table below shows several of these categories. The table 3 result for resolving of good machine simulation deviations. The first set of deviations, 600 plus 170 are closed by the incorrect force list incorrect force behavior. The second set of deviations is 27,205 are because of the last reset to the clock's length in the input stimulus. We added a separate color shadow scope to delay in the reset this fixed or the deviation. The third of the deviations of the 7,722 are because of a sharp delay in RTR. We generate the stimulus using the delay simulation. The fourth set of the deviations, 1,845, are because of the out of the index in 5 phone motors. The fifth set of deviations, 4 are because of the parameters mismatch between the stimulus generations and the good machine simulation, and the design setup is updated to fix parameters of issue which fixed these deviations. The fourth campaign result. The fourth space for Samsung design and exercise is huge. Due to the size of the fourth space, we generate a subset of faults using the statistically random sampling techniques supported by the Kali shadow scope. The total number of the faults analyzed using this technique was 4,598 faults. In the next section, we will walk through the result for this fault list. Table 4 result of fault campaign. We used fully validated the stimulus from good machine simulation, which guaranteed the correctness of the result. We injected a total of 100% of fault, and the result were observation in the 4 categories shown in the table 4. The first category alarm detected means the 65.7% of the faults were detected by a safety mechanism. The secondary category residual, the means 9.86% of the faults were not detected by the safety mechanism and are considered dangerous faults. But this is an exact result since most of the residual faults were injected in unprotected area to do the partially configured safety mechanism on the boundary of the target design. The third category, no deviation, means that 14.98% of the faults were injected but did not cause any deviations in the design for this stimulus. For fourth category, not injected, that means that 9.38% of the faults were not injected because the input stimulus did not allow it. The golden value for those fault nodes matched with that out of the fault value throughout the simulation. The sixth conclusion. Here is the latest experimental result after applying the old method discussed in this paper. The result in the figure 5 that came from the experiment was explained in the previous paper 4. The table 6 shows the updated result after applying all the methods described in this paper, including increasing the stimulus quality with valid setup and cleaned up of the old good machine simulation. The total fault space used for this experiment is represented as 100%, and the total 40% column or other test results are represented as a detected fault ratio of the total fault space. Table 5 is previous result of fault campaign. Table 6 is updated result of fault campaign. And the answering to the question. Are my fault campaign providing accurate result for ISO certification? We described the critical concept and the processes that need to be used for quality fault campaign result. We also addressed the criticality of the handling risks, forces, delays, design setup concerns, and simulation versus synthesis issues. The analysis shown in this paper is based on the Samsung design, where we illustrated how following this methodology described in this paper will help ensure your fault campaign results are accurate. Reference are here. And thank you for your time. Today I led this DVCON2024 paper. Are my fault campaigns providing accurate results for ISO 26262 certification? Thank you for your time, and thank you for your time, and see you next time.